Thank you very much. So we have 25 minutes. It's not a lot, but I'll try to make it exactly on time. So I'll start by giving you some personal info about myself. Then we'll discuss LLM agents in general and what those are. SpawnFest, which is a great contest. Too bad not many people know about it, and I think after this talk more people will know about it. I'll describe to you some gotchas that you need to know when you try and implement self-healing software agents using Elixir, and I'll do a cool demo. Well, I believe it's cool. Now, before I start, just a couple questions to the audience. Who here uses ChatGPT? Awesome. Who wrote applications that use LLM? Okay, not that much. And who tried to fine-tune an LLM? Okay, you're very smart. Okay. So my professional background, born and raised by C++ 98. I'm that old. Did a lot of software development, specifically 3D engines, image and video processing, UI, desktop UI, distributed embedded systems, robotics, and AI, obviously. Work across different industries, defense, telecom, fintech, customer engagement, and right now in the semiconductor space. After a while doing hands-on development, I moved to the product and engineering management. But I did had an opportunity in the summer of last year to go back to the hands-on development. And I was looking for a way to develop web applications, but similar to how I was developing back in the day using C++. And in C++ you can develop everything, right? From the desktop UI to any backend type of software. And when I looked at the web frameworks, I saw that you actually need to use different programming languages and glue a lot of open source tools just to get this web app out the door. So I went looking for on the internet, and I was enlightened by Stack Overflow survey in 2022, where I found this Phoenix LiveView web framework got a top spot. I looked into it, and lo and behold, it's apparently a unified framework with the Elixir language as a backend that got second spot at the same survey. And this is what I was looking for, right? It's especially wired for my C++ brain. So I started to learn about the language and the Phoenix LiveView framework. You can reach out to me on LinkedIn. You have a link here, and the code for the talk is available on GitHub, of course. So first, some introduction into the large language models. There is a lot of action that is happening in this space, specifically in the various coding copilots. I think there is no software engineer that doesn't use some kind of copilot, be it ChatGPT through the web interface or Amazon Q that is embedded into the VS Code and so on. And there are a lot of more niche AI assistants that are based on the LLMs that focus on different areas of software development. So there are agents and assistants for the code review, testing assistants, DevOps, security. There are even assistants that allow you to create UIs from scratch. The most sophisticated agents that are being developed right now are automated coding agents. So you basically give them a task, like a product manager, and they create the full project from scratch for you, including setting up the project, all the dependencies, the right code, they write tests, and they validate that everything works. And there is, of course, human in the loop. And it's in the very early stages, but in the short to medium term, I believe it will be in a much better state and can be used extensively by the enterprises. So if we look at these agents and we zoom in, what are the major architectural components of the LLMs? So obviously, of course, we have the large language model that receives text as an input and it gets text as an output, and it's responsible for the reasoning part, basically completing the task and figuring out what needs to be done. It has to be paired with the memory, so the LLM has the memory of what it's done and it can adjust its reasoning accordingly. And if you want the LLM to be able to interact with an external environment, there is a need to provide tools to these large language models. So by using these tools, they can interact with the external environment via some actions, get the results back, and adjust the reasoning accordingly. For majority of the assistants that I mentioned previously, the task usually comes from other humans, right? So you give it a problem to solve, and it goes and does its magic. Of course, I was learning Elixir and Phoenix LiveView, and I got exposed to this wonderful ecosystem and the great community. I thought, what about if we take the LLM, which is, again, this new brand concept, but we take an LLM and we train it on your tech stack of choice, and we also train the LLM on the domain-specific data of your application, like the business rules and the tests that you usually run, and so on and so on. And we also pair it with the tech stack that has some things that I believe are extremely necessary and help a lot for any development of the large language models and agents. So we need the tech stack to be preemptive, support concurrency, application level fault tolerant is extremely important. You don't want your agent to crash and there is nothing happening afterwards. Flexible inter-process communication, scalability, network distribution, and of course hot code upgrades. I think this is a super unique feature of any BIM language. And then I read on the internet about the SpawnFest and the live hackathons. I never miss an opportunity to participate in a hackathon at the organization that I worked for, or try and participate at other hackathons in general. So this one specifically was at the end of October. My wife graciously agreed to spend the weekend with the kids and let me participate in the hackathon. I did promise to share the spoils if I win. So on the first day of the contest, I've decided to take the large language model and the Elixir and the whole BIM technical stack and create what I call an Open Elixir Intelligence. Okay, so we already have an Open AI, so how about Open EI? And the purpose here is to create an agent that can generate the working Elixir code. Because the ChatGPT and all other LLMs, they didn't have enough data available on the web to be trained on the Elixir. So the code they produce is usually not correct, okay? And you need to copy-paste the code, and then you paste the error, and so on. And I was very deep into it because I was learning the language. So I've implemented this agent. It receives a user request. It generates the code and the tests to validate that the code works. And then it uses the built-in capabilities of code eval string that compiles and evaluates code in runtime. And I capture all the warnings and the errors. And if there are any, I ask an LLM to generate the new and updated code. And we go to step 3. And this happens automatically. It doesn't require me to copy-paste the code, to copy-paste the errors, and etc. Basically, LLM loops until it finds the correct solution, and it gives it to me. So this was the first day of the contest. I did it much faster than I expected. So we're thinking what I can do during the second day of the contest. So I decided to create a multi-agent system. If I already have an agent that when it receives the task, it can produce the correct code, how about I create another agent that will catch any exception or any errors that are thrown by the application, compile it as a task, okay, and ask the previous agent to generate a solution, and once the correct solution is generated, do a hot code load of the solution. So the flow here is this agent monitors the application and catches any exceptions and errors that are thrown by the application. It loads the relevant source code from the repo as a context. It generates analysis of the exception and the source code, possible issues, the list of solutions, what is the best solution, and how to test this solution. Sends this as a task to the agent that I described previously, which comes up with the right solution and sends this back. And this agent, self-healing agent, applies the solution to the relevant part of the code at runtime using code compile string, and then performs code reload via code load binary. And some people thought that this is a great idea, so I did get a second place. I won some, prizes, and I shared the spoils with, my family. So I got the permission to participate in the next year's SpawnFest, by the way. And if we look at the high level at the system architecture, so you have an application, whatever it is, right? And on the side of the application, you have these two agents that are running. One basically monitors the health of the application. And if there are any issues, ask the other agent to come up with a solution. And this agent comes up with a solution in a sync way. And once the solution is ready, sends the solution to the self-healing agent that applies at runtime the relevant fixes to the application. Of course, there is a small issue. The LLM agents are very chatty, okay? Because it's text in, text out, and there is a lot of source code that is being generated. It's very hard to actually understand what's going on when these agents start communicating between themselves, trying to solve the problem, and they usually cannot solve the problem from the first go, so it usually takes some loops. So I utilized all the tools that we know and love here. So specifically, Phoenix pops up. So the communication between the agents is on the message bus. And I've put in place the summarization agent. It's another agent that monitors all the communication in my multi-agent system and summarizes it in short, like bullet points, and publishes it on the Phoenix pops up. And then there is a human-machine interface that the operator can use to see what the agents are doing inside the system, what they're fixing, and so on. So a few gotchas, okay, that you don't see until you start to do that. So whenever you try and generate the fix at runtime, you need to do it in a different namespace. Otherwise, you basically rewrite your original code and everything breaks. As a consequence of that, because the LLM actually needs to do a number of loops and generate the number of times the code, you need to clean up after every evaluation. Otherwise, there are warnings that are being thrown, and your self-healing agent tries to fix these warnings. There is a privilege awareness. The code evaluation and the code compile string and so on runs with the same privileges as the Beam VM. So please don't ask the agent to wipe your file system. It will gladly do that. And you, of course, need to capture not just the exceptions themselves, which is the easy part, right? It's just, try and catch and so on. But you also need to capture the warnings that are thrown when you compile your code, and those go to stdr. So I used capture.io to capture this stdr output and give it back to the LLM. Source code updates. So if your source code has a number of issues, but the LLM fixed only one issue, you do need to update the context repo with the relevant source code and so on, because if there is another error in the same code and you did not update the context repo, it will load the code with all the errors that were not fixed previously. Concurrency limitations. LLMs are not as humans, at least not now. So you cannot really have multiple agents working on the same code base, fixing, let's say, errors in the same module. Imagine asking LLMs to do, the merge, right? So we as humans struggle with it quite a lot, and trust me, LLMs will struggle much more. LLMs, they also go off rails quite frequently, so you need to monitor and make sure that they move from step to step and they don't lose the context and the state and so on. So for instance, an LLM can provide you, after a couple of loops, can provide you the working solution, but it will forget to provide the tests, okay? So there is some gentle reminder that you need to give to LLM that please provide me the test. You forgot about it, and LLM will say to you, oh yeah, sorry, okay, I apologize, and then we'll give you the right stuff. And of course, because LLM, it's text in, text out, and it learned on a lot of data from the web, and data on the web is, of course, Markdown. Whenever it generates code, it tries to wrap it with Markdown tags. So you do need to do some, basic text processing and cleanup and etc. Otherwise, you will try to compile your code with the, Elixir Markdown tags. Demo. So who here saw the video of Sasha Juric, Soul of Erlang and Elixir? Raise your hand. That's it? Okay, please, after the conference, go and watch the video. Okay, it was 5 years since this video was released, and it's an incredible video, and this is one of the first videos I saw when I actually started to get exposure to Elixir and so on. And I got permission from Sasha to use the code from his talk here to present the demo. So what Sasha actually tried to do is to show the preemptiveness, concurrency, and capability of the Beam VM and Elixir, and how you can actually debug if you have an issue. So in his demo, there is a load simulator and a monitor, and we can spun up 10,000 jobs that will be performed successfully per second. And there is a task to calculate the sum of n integers using task async. But the code that calculates the sum of n integers has some issues. So first of all, when you enter 13, it throws an exception. It's issue number 1. Issue number 2, the sum is implemented as a recursion, which is not very good performance-wise. You give it a big number, it takes a long time. And if you enter a negative number, it's an infinite recursion, right? So there is a task that takes 100% of CPU and never basically releases it. So what I would like to demo is to take these self-healing agents that I just described to you and pair this with this demo system that Sasha had created and put in place. And if we do that, our system is going to look as follows. So we have the self-healing agent, we have the fix request resolver, we have summarization agent and an HMI, so we can actually see what's going on inside the system. And our core application is basically the application that Sasha wrote. It has the UI where you can enter the integer and it will calculate the sum. It has a math module where all the errors are. This is why it's in red. And we also have a monitoring UI and a load control, so I can spin up 10,000 jobs and demonstrate to you that, you know, just like Sasha fixed all the issues and the jobs were executing successfully, I can have a LLM agent that is going to do the same and utilize all the preemptive capabilities of the VM. So taking the overall system architecture of the large language model, okay, let's look how the design looks right now when we actually implement it. And our agents are, of course, gen servers. The memory of the agent is the state of the gen server. We have an LLM that is responsible for reasoning, and I'm using a GPT-4 of OpenAI here. And because we need this agent to interact with the external environment, we give tools to the agent. So first of all, we give a pub sub, so agent can communicate with the front end or with another agent. We give the agent the context repo, so it can extract the source code to be fixed and so on. And we give the agent the same information and tools that Sasha used in his demo. So it's trace, stack, trace, and top. So it can figure out why the task takes 100% of CPU and so on. And we give the runtime evaluator tool through which the agent can compile, evaluate the code, get all the errors and warnings, and try and fix if there are any issues. But in our case, of course, the task is not coming from a human. Okay, the task is coming from an exception catcher module that catches all the exceptions and errors that is thrown by our application. CPU usage monitoring. This is a task that runs and monitors the CPU usage. And if some process takes 100% CPU, he pings the LLM and says, "Okay, look up what's going on." And of course, one LLM talks to other LLM. Okay, but there is no human in the loop. And what you're going to see on the demo, I recorded this, okay, because the LLM is not always successful, and I'm bounded by time. Okay, so you will see the recording, but of course code is available on GitHub, and the fonts, if they're small, you can use the screens on the side, I think. So in the UI, and those of you who have seen the video will recognize the UI, and those who have not seen the video, once you see the video, you will recognize the UI. This is the Sasha's application. On the right, there is a UI that allows me to create a fake load of, let's say, 10K jobs that have to be executed. And there is a chart showing successful executions of the jobs over here. The schedule of the CPU usage is down below on the right. This is the front end where you enter the integer, and this is the calculation, the sum of n integers. And in the middle, you can see here the output of summarization agent that is going to monitor the communication between the multiple agents that we have and provide the output. So let's see. So this is a web UI. You need to go to the portal and turn the self-healing agent on. From this point on, this agent monitors everything that's going on. Let's see that if I enter a number, I get the sum, and all works as expected. Now let's create a fake load. let's run 10K jobs, and let's see that the jobs are getting executed, and we can still enter numbers, and this is like preemptiveness and concurrency and so on of the beam, and we get the correct result. And now I'm entering -1. And you can see that down below, oops, sorry, wrong button. Yeah, you can see that right now, if I enter -1, the chart, the schedule usage down below on the right will spike. So it means that we have a process that takes 100% CPU. And once this is happening for a certain period of time, there will be an event sent to our self-healing agent. Okay, look into it. So this is the issue, the event that our large language model got. It has the error. There is a task that's consuming high CPU. And the agent on the background, it goes to the context repo, it pulls the source code, it tries to analyze what are the issues in the code, it tries to list all the possible solutions, tries to choose the best solution available, and create tests to validate this solution can actually work. Then it packages this as a request and sends it via a pub/sub to another agent that is responsible for coming up with a fix for this specific issue. And this is going to happen in a second, and there will be different colors indicating different agents that we have that run in the system. So you can see that the blue color represents the fix request solver agent. It tries to come up with the correct way to solve this, and then it's going to run some tests, and it will get the result of the run of these tests. So you can see here that the agent actually came up with a solution in the LLM evaluator namespace. It runs some tests, and there are no errors and warnings, and the code execution is successful. It provides the output. And right now it compiles a message which is called working solution and sends it to the self-healing agent that is going to take it and is going to do a hot reload at runtime. And once the hot reload happens, the process that takes 100% CPU time is going to be killed. As you can see right now, the schedule usage dropped, and the agent says that hot code update was successfully applied, and the issue was solved. Now let's validate, maybe this was not solved, right? Let's go back and let's try and enter a negative number. And we can see that there is an error message. And if I put 13, which was thrown in an exception previously, right now it does not throw any exceptions. And during all this period in time, we still had 10K jobs being executed successfully. So the roads not taken yet, but they will be taken, and maybe someone will participate in the next Spawn Fest in October this year and actually implement this. So it's quite easy. So for instance, you can have an agent that is going to add functionality to itself. And the beauty of Elixir and OTP is that OTP is a safety net, right? Agent tries to change itself, it crashes, and then it can come up and see why it crashed and fix its own source code. We have a multi-agent system, right? And we have one agent that catches the error, and then it asks other agents to perform fixes, and preferably in a different environment. So here we can use Flame to actually spin up fix request solver agents and have a segregation, not just in the namespace, but also physical segregation. And then the fix will be communicated to the self-healing agent that will apply the solution at runtime. And of course, for all the new guys and gals that are learning the Elixir or any other Beam language, having a live book component that whenever you ask to generate a code, it basically generates the relevant code within your application context is very helpful endeavor. So this is the last slide, and I hope it leaves a taste of like future possibilities with LLM and the Erlang and the Beam. Thank you.
That was amazing, Vlad. Thank you very much. Questions?
So when it comes to exceptions, it's very common that one error spawns a multitude of those exceptions and error logs. Do you do some grouping or root cause analysis, or does the self-healing agent try to fix every single one independently?
LLM actually can understand that the top exception is usually like the first one is, LLM can understand what is the original exception, basically. So I don't do any specific cleanups. But of course, this is not a production system. It's like a result of a hackathon. So some caution needs to be applied here. Yeah.
There was a question over here. Oh.
Thank you very much for the talk. As far as I understood, you just took a junior developer and put it into Beam, who is fixing bugs just on the fly.
Exactly, you're on me here. Yeah.
Though I have a real question. How many times your agent need to ask ChatGPT for correct code until it give up?
Well, you see, the LLMs are not deterministic. Okay, and they specifically have an issue with Elixir because there is not enough data. If it was Python, it would have been much easier. But it fails quite a lot depending on the complexity. So if you try to give it a list and reverse a list for me, this is easy peasy. But if you do some complex stuff, and whatever I showed to you right now is a complex stuff for the LLM, it fails quite often. It fails quite often. But if you take an LLM and you fine-tune the LLM just on the Elixir, let's say, language, okay, and the programming ways and how to solve issues, etc., plus you train it on your own code base, right, then the performance will be much higher. And in my case, I'm also not using like fancy LLM tactics like, multi-shot, learning, and then so on. So it's rather straightforward, but it demonstrates the concept and the possibilities ahead of us. Yeah.
I think we have time for another question, if there is one. All right. Thank you very much, Vlad.
Thank you.